All right, we're about to work on a monster problem right now. Sample problem 3.20, 320 deals with calculating quantities in a limiting reactant problem. So truthfully, this is the reality of how most things are going to work, right? And when we do a chemical reaction, we're mixing two things together and we're going to have something that runs out first, right? We used a lot of baking or food examples in class, but the idea is you're not going to have perfectly what we call stoichiometric amounts, exact amounts of each of those, right? You go to bake cookies in your kitchen and you're going to pull the flour out, pull the sugar out, pull the eggs out and everything with the exception of the eggs that you count quantities, right? You might use up exactly the 2 eggs that you have to make cookies, but you're not going to have exactly 1.5 cups of flour and exactly 3/4 of a cup of sugar, right? So you're going to have something that's left over. And the idea is we're going to be limited in terms of in our kitchen how many cookies we can make by whatever we have. That's our limiting reactant. So just looking at some definitions here that are on your sheet that you have here, limiting reactant problems happen when one reactant limits the amount of product that we form. Limiting reactants are completely used up in the reaction, and anything else that's a reactant will be in excess. That is, it's leftovers. You know you have a limiting reactant problem when they give you amounts of more than one reactant. And that's a really important thing because I think everybody starts panicking like every problem is going to be a limiting reactant problem. Well, if they only give you the amounts of one reactant and either tell you that the other is in excess or you can assume that the other is in excess, then that's not the case. There's 2 methods that you can calculate who is a limiting reactant. The first method is called how much of other reactants do you need? But since your book uses the second method, which makes more product, that's the one I consistently use in working through our problems, so that's the one that I will use. At the end of the day, I don't care which one you use, as long as you use one consistently that makes sense to you. Part of this problem, too, is creating a reaction table, or what we call an ICF table, initial, change, and final, that helps keep track of quantities in limiting reactant problems. So there's a separate handout that we had here that kind of looked like this, where it had actual slides here that talks about how to make up a reaction table, an ICF table. So I'll refer back to this again as we do our problem, but it also shows the 2 different methods for calculating limiting reactants. So again, we're going to implement this in this next sample problem. So this video is going to be a little bit lengthy because working through limiting reactant problems is again an essential skill and an essential component to stoichiometry problems. Okay, so we ready? Here we go. So this problem really, again, pulls a lot of stuff together because they give us information in words. So we first have to actually start with formulas, right? So again, a chapter 2 skill again, just like we had in our last problem, right? In our last problem, sample problem that we worked through 16, we had to take formulas and get a balanced chemical equation, and then we could begin to do our math. So the same is going to kind of be true here. We have to take these formulas and we have to put them into a balanced equation. Okay. And then once we have our balanced chemical equation, we need to figure out who is our limiting reactant. So LR is what we kind of use as an abbreviation for limiting reactant. And once we do that, then we're ready to finally answer our question, which is how many grams of nitrogen gas are formed. So they're asking a question about how much product we form. So again, we have to first start by creating a balanced chemical equation. So problem is, a fuel mixture used in the early days of rocketry consisted of 2 liquids, something called hydrazine, N2H4, and dinitrogen tetraoxide, N2O4. These ignite on contact and we form nitrogen gas and water vapor. So we kind of have to put these 2 together. So we've got N2H4, let me put hydrazine first here. N2H4, so this is our hydrazine. Okay, they tell us that these are both liquids, so N2H4 liquid reacting with N2O4, again another liquid, so that's our nitrogen, dinitrogen tetraoxide. These ignite on contact and they generate nitrogen gas, which again, it's important that you know that nitrogen gas is N2, and then water vapor. So H2O, and they tell us it's vapor, so that's gas. Okay, so again, now we need to balance this chemical equation. So going through here, I might balance with hydrogens first, right? Because we can see that we've got 4 hydrogens over here, and we've got 2 over here, so you might consider balancing that first, or you might look at nitrogens. Let's look at nitrogens here. We've got 4 nitrogens, and we only have 3 that are over here. So again, if we go and we balance our nitrogens, we could put a 2 here, right? Going and balancing our hydrogens now, we've got 2 that we need to put over there by water. Again, but now we're going to see that we've got 2 oxygens, and we need 4 of them over here. So again, we'll have to go and make this be a 4. And you see how balancing can kind of go back and forth. Now we've increased our hydrogens. So again, we're going to have 8 hydrogens. So I'm going to need to put a 2 there. Oh boy, that now changes my nitrogens. So I've got 4 nitrogens plus 2 is 6. Now this needs to be a 3. All right, let's go and just check and make sure that everything's good. 6 nitrogens, 6 nitrogens. We've got 8 hydrogens, 8 hydrogens. 4 oxygens, 4 oxygens. Okay, check, we're balanced. So again, just another example there of balancing chemical equations. A lot of times it might be iterative. You might have to go back and forth. All right, once we have our balanced chemical equation, now we're ready to determine who our limiting reactant is. Now, why I like having chemical equations that I write materials underneath is it's going to be an easy way for us to see that this is a limiting reactant problem. It tells us how many grams of nitrogen gas form, so that's our where do we want to go? That's our question. How many grams of nitrogen gas form when we have, this is 100 grams of hydrazine, so we've got 100 grams of hydrazine and 200 grams of our dinitrogen tetraoxide. So we want to know how much of this do we make. Now, alarm bells should go off in your head if you see that they are giving you amounts of 2 reactants. Because see if this makes sense to us. We can go on a walk and take this amount and go using molecular weight to moles. We can use our balanced chemical equation to get to moles of N2, and then we can find out how many grams of N2. But we also could take the same walk with this guy. Equation, and then a molecular weight. So the question becomes, which walk do we take? Well, truthfully, we're going to take both of these walks. Okay, and the reason that we're going to take both of these walks is only one of them is going to create the smaller amount of nitrogen gas, and that is our limiting reactant. Again, just go back to your kitchen analogy for a second. Imagine you had a giant bag of flour and a giant bag of sugar, but all you had was 2 eggs. It doesn't matter how much flour you have, that you could make 20 dozen batches of cookies with the flour or 10 dozen batches of cookies with your sugar. All you have is 2 eggs. So you're limited by that, and you're only going to be able to make 1 batch of cookies. Okay, but we need to kind of take each of these on. And an important skill to remember is we need to actually, we're going to use method 2 here. We're going to convert each of these reactants into moles of product. And we'll compare those. And whoever makes the least moles of product, oops, and I circled the wrong one here. Whoever makes the least moles of product, these are going to be the ones that we're comparing. Those are going to be the ones that will be the limiting reactant. Okay, so let's walk through this, and hopefully this will make sense. And we're also going to be simultaneously setting up stuff to write a reaction table for the process. Okay, so the first thing that we want to do here is we want to take this first walk. So we're going to have our walk for hydrazine, N2H4. So we've got 100 grams of N2H4, okay? We use the molecular weight of this, which is 32.05 grams of N2H4 for every 1 mole of N2H4. And again, to remind ourselves where we get this information, this is our molecular weight, okay? The reason I'm actually going to stop this calculation at this point is I'm going to get a piece of information that will become part of our reaction table, okay? This means we have 3.12 moles of N2H4. Again, why I'm stopping here is this is useful for our reaction table. we'll make our reaction table on our next piece of paper here. We need to change who we're talking about, right? We talked about using a chemical equation. So we're going to have 2 moles of N2H4 for every 3 moles of N2, and that gives us 4.68 moles of N2 that could be made with the amount of hydrazine that we start with. Okay, now let's do the same walk for our dinitrogen tetraoxide. Okay, so in this case we have 200 grams of this species, N2O4. We need to convert that into moles, so the molecular weight is 92.02 grams of N2O4 for every 1 mole. Again, this is molecular weight. I wanted to label up here. This is from our equation. That's where we get that from. This ends up being 2.17 moles of N2O4. And again, this is going to be useful information. We're going to put this in our reaction table. Using our balanced chemical equation, 1 mole of N2O4 makes 3 moles of N2, and so we've got 6.51 moles of N2 that we could make from this starting amount of dinitrogen tetraoxide. We're going to pick the smaller of these numbers, and this becomes our limiting reactant. So a couple of important things to note. Okay, we cannot use the amounts of the reagents to determine our limiting reactant, right? Well, maybe you would have gotten lucky if you said 100 grams versus 200. Oh, this guy's going to be the limiting reactant. You would have gotten lucky, though. Even if you did the correct step and converted these to moles, you do have fewer numbers of moles of dinitrogen tetraoxide, but that doesn't mean it's a limiting reactant. You need to use how it's used in the balanced chemical equation. Because we use twice as much of our hydrazine as we do our dinitrogen tetraoxide, even though we have more of this in terms of the total number of moles, because we need to use twice as much of it, we don't make as much product from that amount of N2H4. So this guy is our limiting reactant. So again, limiting reactant problems can be, pretty involved, right? Just even to determine the limiting reactant. But one of the skills that I want to make sure that you learn well in general chemistry, and part B of this problem, is how to write a reaction table for figuring out. Now you could answer this problem, you could answer how many grams of nitrogen gas form. You could answer that problem by just using the molecular weight of our nitrogen gas and getting to grams of nitrogen. You could solve that problem immediately from right here, and I encourage you to do that. But an important skill that I want you to learn, an important skill that you will be tested on, is how to write a reaction table. And why I'm doing that is using reaction tables are essential for Gen Chem 2. Okay, so I'm going to put another piece of paper up here, and we're going to finish out this problem by making our reaction table. Okay, so again, if you need to, go back and kind of review these sheets here, this handout that we had here on how to create a reaction table. We write our equation on top. We make 1 column for each species in the equation. We're going to have 3 rows for initial, change, and final. The initial values are going to be essentially the initial moles that we have. That's why we stopped this problem right here. These values are going to go in. And as I have indicated here, the most error-prone step is determining the change column. So again, we're going to use positive and negative signs to indicate if something's appearing or disappearing in our reaction. And our coefficients from our balanced chemical equation will allow us to propagate values in our change row. All right, so hopefully all of that will make sense as we implement it here. All right, so as we just discussed, the top row of our reaction table is our balanced chemical equation. So 2N2H4 plus N2O4 make 3N2 gas plus 4H2O gas. Now, the quantities that we always have in a reaction table are moles. And again, that's why I stopped these calculations here, because knowing we needed to make a reaction table, I was going to need that data anyway. So the first row, again, is our balanced chemical equation. We have three other rows, which are initial, a change, and a final row. And so columns represent these initial, change, and final values for each of these species in our chemical equation. So under the initial column, we always have zeros for our products because we haven't formed any yet. For our reactants, we're going to put these numbers in directly as we calculated them. So there's 3.12 moles of N2H4 and 2.17 moles of N2O4. Again, I'm not going to put units with them because I know that only moles go in my reaction table. So an important thing to point out that sometimes students get confused. Sometimes students will see this 2 here and they'll want to multiply this by 2 and have like 6.24 here. You don't want to do that. Whatever the quantity is that you're given, once you convert it to moles, that is the exact number that goes in here. Now, again, calculating who is the limiting reactant is important, and we figured out that it was hydrazine. So I'm going to put a little LR above this column because that reminds me that that species is the limiting reactant. And now I know that everything else is going to be based off of that reactant. Okay, so the limiting reactant kind of determines how everything else gets propagated. So we know that the limiting reactant is the species that gets used up. So when I make my change row, I start with this species. So we're going to lose 3.12 moles of our limiting reactant. So whatever we had initially, we use it all up. So again, I'm going to put a little star here. This is the column that you start with. So you begin with the limiting reactant spot in your change column. So everything else in our change row, I should say in our change row, it's not a column, it's a row, in our change row is based off of our limiting reactant. Okay, so limiting reactant always gets used up, so it's going to have a 0 in our final column. Okay, so now how do we go and figure out what goes here? I'm going to kind of show you through a couple of calculations quickly how this happens. So if we have 3.12 moles of N2H4 and we want to change who we're talking about, we want to get rid of moles of N2H4 and we want to change who we're talking about and have it be N2O4. Okay, in this case, we use our balanced chemical equation, and there's 2 moles of N2H4 for every 1 mole of N2O4. So I can see here mathematically, I'm going to divide this by 2. So that's how I'm going to get 1.56 for this guy, and again, that goes away. Now, a good check to make sure that you don't use this 2 in the wrong way and double it. If you doubled this and you got 6.24, when we would try to subtract that from here, we'd end up getting a negative value. And that's a big sign that you made a mistake. You should never have negative signs in your final row. Again, this is another reactant, so we know it's going to be disappearing. This 1.56 came from the fact that we use half as much of this reagent as we do this. Okay, so again, if we subtract these, we get 0.61. There's this left over. Okay, or what we call excess. That's the chemical word. Okay, I'm going to do the same treatment for what we have over here. Okay, this one might be a little bit harder to see. We could easily see that this was half. We're going to see that this one's going to be double. I'm going to walk through the same calculation so you see exactly what you need to do for here. 3.12 moles of N2H4, again changing who we're talking about, uses a balanced chemical equation. So 2 moles of N2H4 makes 3 moles of N2. So again, we're going to get 4.68 for this. That's how much nitrogen is appearing. You'll note this was the same number we calculated up there. Okay, so we already kind of figured and we could see in our head that this was going to be a doubling. So this is plus 6.24. Kind of taking, and sometimes we have this kind of as a whole line here. So 1.56. We'll be making 4.68 moles of N2 and 6.24 moles of H2O. And again, just a little side note here, this is the same as we got for a limiting reactant calculation. So that's a good kind of internal check that we're doing stuff right. And the last part of this problem is to finally answer the question we had from part A, how many grams of nitrogen do we make? But again, that's based off of the limiting reactant. So we know we're going to make 4.68 moles of N2 gas. So again, we can take and we can convert that using a molar mass of N2. So again, 1 mole of N2 is 28.02 grams of N2. Calculation for this gives us 131 grams of N2. So again, this is the answer for part A. Part B had us draw a reaction table. So this is what a reaction table looks like, also called an ICF table. Initial columns from moles of initial quantities we had. Change column begins with your limiting reactant and gets propagated. The values that are propagated are dependent on our balanced chemical equation. The final column is really just the addition of our initial plus change. 0, 0.61, 4.68, and 6.24. Again, limiting reactant problems and reaction tables are two kind of involved skills, but essential to managing stoichiometry problems, and again, important skills that we'll use again very heavily in Gen Chem 2.